Welcome to the fifth lesson of MATH2. In this lesson we're going to look at the dot product in the linear algebra section, and we're going to look at the finite state machine in difference to the finite state automaton in the language section. So let's start with the linear algebra part. First, a small repetition. So we have a plane represented with an equation. The equation would be 3x plus 4y minus 2z equals 6. How do we get to the vector form of this same plane? Okay, hopefully you remember that a vector form has this shape. So we have x, y, z being some starting point plus lambda times one direction vector plus mu times another direction vector. To get this point and the two direction vectors, we need to find three different points of the plane which are not in one line. So let's see. If I find x being 2, then 3 times 2 is already 6. So the other two elements I can choose 0. So 2, 0, 0 would be a good point on this plane. Well, if we figure out another easy point, I could think of y being 1 and x 0. If y equals 1, then I have 4 minus 2z equals z. So that would mean z would be minus 1. So another point would be 0, 1, minus 1. Okay, now I need a third point. And let's just make x and y 0. Then minus 2z would be 6. So that would be minus 3. So I have 3 points on this plane. One of the points I will use as a starting point. And then for the other two direction vectors, I have to have a movement from one point to the other. So let's first go from 2, 0, 0 to 0, 1, minus 1. So that means I have to go minus 2 in the x direction, plus 1 in the y direction, and minus 1 in the z direction. Well, for the next one, I could move, for instance, for the second point to the third point. So that would mean 0 in the x direction, minus 1 in the y direction, and minus 2 in the z direction. Okay, we still have to see if these two vectors, so the two direction vectors, are not depending on each other. And as you see, in this one, I have a 0 on the x position. So this one, the first one, can never be dependent on the second one. And minus 2 will never be lambda times 0. So this is a very nice vector form of the plane given with 3x plus 4y minus 2z equals 6. Another exercise. So we have a line L given with a starting point plus one direction vector, and we have a line M giving with a starting point and a direction vector. And they ask us a vector form of a plane parallel to both lines through the point 3, 2, 5. Okay, so x, y, z would be, we have a point on the plane because it has to go to 3, 2, 5. And then we need to find two direction vectors to represent this plane. Okay, but they just told us. And they said line L is given with a specific direction vector, this one, and line M is given with a special direction vector. So I can use these two to represent the plane. So 2, 1, 1, minus 1, 1, 2. Okay, we only need to check whether indeed the vectors are independent. So let's see. 2 would be minus 2 times minus 1. If I then use this minus 2 in the second part, 1 equals minus 2 times 1. Well, of course, that's nonsense. So indeed, we have two independent vectors, and this would be a vector form of a plane parallel to line L, parallel to line M, and having a starting point 3, 2, 5. Okay, the new subject for the linear algebra part of this lesson is the dot product. And the dot product is indicated with, yeah, as the name says it already, a big dot. And if we calculate this dot product, then the result tells us something about the sizes of the vector. Maybe you remember that this was the size of vector A, the length of vector B, times the cosine of the angle between the two vectors. So for instance, if I have a vector A and I have a vector B, then this dot product tells us something about the cosine of this angle. Well, to refreshen, what is the cosine? If we have the unity circle, this is the x and this is the y, we have a vector A, then the cosine of this vector is the projection of this vector on the x-axis. So that is this small part, so the projection of the vector to the x-axis. This is the cosine. If we would look at the projection on the x, on the y-axis, this would be the sine. So the sine is the projection on the y-axis and the cosine is the projection on the x-axis. Okay, so what would that mean if I have two vectors which are perpendicular? So they have an angle of exactly 90 degrees. So what is the cosine if I project, in fact, this vector here on the x-axis? Okay, then you would say, yeah, it just drops down. So the projection would result into 0. Okay, and if we see this one, then hopefully you get a nice feeling about this dot product. So apparently, if the cosine of two vectors is 0, then the dot product is 0. So the vectors are perpendicular in that situation. Okay, that's all good and well, but how do we calculate the dot product? And now that's even nicer. There's a very simple formula for that. So if we have two vectors in a 2D space, then we can just find the dot product by multiplying the x coordinates and the y coordinates. So for example, if we have a vector 2, 1, and we want to take the dot product with a vector, let's say 1, 3, then the result would be 2 times 1 plus 1 times 3 would be 5. Okay, so if I can calculate it so easily, then I can apparently check very easy whether two vectors are perpendicular. Because as we've seen in the last slide, if vectors are perpendicular, the dot product would become 0. Okay, for instance, if we look at the vector 1, 0 and 0, 1, yeah, you can see from sight that these are indeed perpendicular. And let's check it. So 1 times 0 plus 0 times 1, and indeed that is 0. So these two vectors are perpendicular. Let's check another one. For instance, the vector 2, 1 and the vector minus 1, 2. So if I make a drawing of this one, the vector 2, 1 would be this one, and the vector minus 1, 2 would be this one. So it looks quite perpendicular, huh? So this looks like an angle of 90 degrees. So let's check it. Let's do the dot product. So that would give us minus 2 plus 2, and then indeed the dot product calculation gives us 0. In 3D space it's just as easy. Just multiply the x's, the y's, and in this case also the z coordinates. So, for instance, if we look at these two vectors, we have 0, 0, 1 and 1, 0, 0. It's quite obvious that they are indeed perpendicular. Let's check it with the dot product. So that would give us 0 times 1 plus 0 times 0 plus 1 times 0. And indeed, the dot product is 0, so these two vectors are perpendicular. Okay, these are two vectors which are not as easy to see whether they are perpendicular or not. So let's just give it a try with the dot product. So 1, 2, minus 5, dot product with 3, 1, 1 would give us 3 plus 2 minus 5, and indeed these two vectors are also perpendicular. Okay, another thing we see in two-dimensional space is if we look at an equation which is given, for instance, by 3x plus y equals 5, then the parameters in front of the x and the y can be used as the coefficient vector, the CV, so not the curriculum vitae, but the coefficient vector. So the things in front of the x and the y represent the coefficient vector. Okay, what's the help in this one? So let's first see if we can formulate the vector form of this equation. How did we do that? Okay, we have to find a point on the line. So let's find a simple point. So for instance, if x is 1, and it means that 3 times 1 plus y equals 5, so y would be 2. So the point 1, 2 is on the line. Another simple point would be choose x is 0, then y would be 5. So with the help of these 2 points, we could find the vector form. So xy would be a starting point. Let's just pick one of the two. So let's do the first one. 1, 2 plus lambda times the movement to go from 1, 2 to 0, 5. So I have to go minus 1 in the x direction and plus 3 in the y direction. So this will give us the vector form. And now something amazing happens. If we look at the direction vector of the line and we compare it with the coefficient vector, then maybe you already recognize, if I do the dot product of these two, that the result would be minus 3 plus 3 equals 0. So apparently the coefficient vector and the direction vectors are perpendicular. So we found a complete new and very efficient way to find the vector form of an equation.